Okay, so we're going to start with some definitions, or actually a definition. So we're going to start with reflectional symmetry. So reflectional symmetry means a figure can be divided with a line so that the two sides are mirror images. So go ahead and write that in. The rest of this will go pretty fast. That's the only writing for this page. So a figure can be divided with a line so that the two sides are mirror images. I also like to think of this as folding. The line would be where you can fold it in half and make everything match up. So I have put my name in all capital letters so that we can look at each letter and draw the lines of symmetry. So draw the lines of symmetry for each letter in my name below. So where could I draw a line of symmetry for the A? Just go ahead and say it.
Like that.
Right down through the middle, right. So it would be like this. We could draw a line of symmetry. So if I folded it, this piece would fold onto that piece, this would fold onto that. And so it looks like these are mirror images. The M is the same way, right through the middle. The A is the same way. What about N? Does N have any lines of symmetry?
No.
No, it doesn't have any. So the N's going to be none. I'm going to write that. What about the D?
No.
Yeah, if you could go this way.
Yes, you could go horizontally this way and draw a line of symmetry, and the top would fold to the bottom, so that works. And then we have another A. So that is how lines of symmetry work for just basic shapes. And letters are just kind of a nice study because some of them have lines of symmetry and some of them do not. So when I say none, I should say, actually I should clarify that's no line of symmetry. It does have a type of symmetry that we'll talk about in a little bit, but not reflectional symmetry. Okay, so we're going to look at some basic shapes. We're going to start with a square. So we all know we can divide a square this way, and we know we can divide it this way. Is there anything else?
You can go corner.
You can go corner to corner. If it's truly a square, you could fold it this way, and then this corner folds to that one, and also this way. So this would have 1, 2, 3, 4 lines of symmetry, and you could count them 1, 2, 3, 4, and then don't count them again on the other end. There's just 4 lines of symmetry. Okay, so is the rectangle going to be the same thing? No, it just has the vertical line and the horizontal line. You cannot divide it corner to corner because they wouldn't match up. So this only has 1, 2 lines of symmetry. What about an isosceles triangle? How many lines? 1, just right down through the middle. Because these two sides are the same, they would match up. These two angles are the same, they would match up. What about an equilateral triangle? How many would that have?
3.
So we have the one obvious one, but we could also draw one here. We could also draw one here, because remember it's the same on every side. And I can't draw a straight line, so sorry. Let me try that again. So right through the middle like that. Okay, so it has 1, 2, 3 lines of symmetry. And sometimes for people to see that, they like to turn it and look at this direction. If it's truly equilateral, it'll be the same on every side, and you can do 3 lines of symmetry. What about a scalene triangle?
You can't do anything.
Yeah, there's none. So this would not have any. So this one has no, we'll say no reflectional symmetry. This one has none. There's no place I can draw a line and make that match up. Now this one I want you to think carefully about. What about a circle? What?
Infinite!
Infinite, because we could draw one here, and one here, and one there, and one there, and one there, and one there, and you could just keep going. They should go through the center. I'm really bad at drawing. But there are infinite lines
Can I just draw the infinity sign?
of symmetry. Yeah, you could do that. An infinity symbol. There are infinite lines of symmetry for a circle, And that's because a circle is the same all the way around. So no matter, as long as you were going through the center point, which I did not illustrate very well, but as long as you were going through the center point, anywhere that you folded it, it would fold on top of itself. And it would be a mirror image. Okay, so on the next page, we're going to look at rotational symmetry. So we'll start with the definition. So you have rotational symmetry if a figure can be rotated, which is another fancy way for turned, less than a full turn and look the same as the original image. So there's several different ways you can word this. So, and it should be rotated about a point. I left that part out, so let me pencil that in over here. So it can be rotated about a point, less than a full turn, and look the same as the original image. But basically I want you to know if you turn it and it looks the same, then it has rotational symmetry. So we'll go through several examples and talk about this in a little bit more detail, but first you got to have the definition. Okay, so let's start with the S. So I'm going to say that we're going to pick a point in the middle of the S right here. You can't really see where I just marked that, but right here, I'm going to put my pencil like in the middle right there. And if I rotate it a half turn, okay, if this were a different S, it would look the same. I just realized it's not the same on the top and bottom, but let's pretend it was. I'm going to make this have rotational symmetry by extending this out just a little bit. I intended to use a font that this would be the same. So pretend that this S looked exactly the same on the top and the bottom. I tried to fix it there. So if I rotated on this point in the center, it would look the same this way as it does this way. So this is your rotation point here in the center, and you can turn it a half turn. So this would be, if you turn it a half turn, it has rotational symmetry. So we could say that it has rotational symmetry about 180 degrees. 180 degrees is a half turn, because 360 is all the way around, just like the basketball players do before they dunk it. They do a 360, turn all the way around, and then dunk. Okay. It's just a good visual. So halfway is 180. So the H will be the same way. If you put a point in the center here, and we turn it a half turn, which is 180 degrees, it'll look exactly the same as the original. Nothing looks different. It looks exactly the same. So we could also say that this H has rotational symmetry if you do a half turn or 180 degrees. And then what about this parallelogram? I think it'll be the same thing. If I put a point here in the center, it's not always a center point, by the way, but it could be. So a center point right here, and you turn it. Actually, I guess for rotational symmetry, you would want it to be in the center. I'm thinking about it here. Rotate it, it'll look the same. So these all had half turns. So that's a half turn, 180 degree rotation. And then this one's a little different. Let's say we pick a point here in the center. Would I have to go a whole half turn to make it look the same? I could just turn it sideways and it looks the same. I could turn it again and it looks the same. I could turn it again and it looks the same. So there's actually 4 different places it's going to look the same. So with this one, I only have to go a quarter turn,
90 degrees.
which would be 90 degrees. You're right. If you turn it 90 degrees clockwise or counterclockwise, it's going to look the same. Okay? And so what they call that, if there's 1, 2, 3, 4 places where you could turn it and look the same, is they call that fourfold rotational symmetry. And so these that were half turns back on this side would all be twofold rotational symmetry, because there's only two places that are going to look the same. They look right when they're upright, and they look right when they're upside down, and that's it. But this one looks the same if it's like this. So that's 1, 2, 3, 4, and then you don't count it when you get all the way back. So that would be called fourfold rotational symmetry. Okay? So down here, we're going to define what a regular polygon is. Does anybody know what that is? Regular polygon? No. Do you?
It just means it's a polygon with sides and it doesn't have no sides.
No. So that's just what a polygon is. If you put the word regular in front of it,
Is it commonly used?
no, it just means that all the sides are congruent and all of the angles are congruent. So the one that we talk about most often with this would be an equilateral triangle. So here's an equilateral triangle. So I'm going to put that underneath, which we've already talked about this year, but it doesn't hurt to review the vocabulary. So here's an equilateral triangle. The sides and angles are all the same. So what kind of rotational symmetry will it be if we turn it about the center point? So here's one place, and if I turn it this way, it'll look the same. And if I turn it this way, it'll look the same. So what do you think, Tommy?
Threefold.
So it has threefold rotational symmetry. He just had his hand up first. He was being so patient. So, who wants to tackle the square? So you did one. Who wants to do the square?
It's a fourfold.
It would be fourfold. Awesome, because you could turn it and you could have this side on top, this side on top, that side on top, or that side on top. It'd have fourfold rotational symmetry. And then what about this pentagon where all the sides and angles are the same? You see a trend? 3 sides, 4 sides, 5 sides. What do you think?
Fivefold rotation.
Yeah, and they just call this a regular pentagon. That just means all the sides and angles are the same. So that would be fivefold rotational symmetry. And then this last one, what kind of a shape is this? It is an octagon, so it's a regular octagon. So it would have eightfold rotational symmetry.
That's the trick. You can just count the sides.
If the sides are all the same. So this works with regular polygons. With things like a parallelogram, that didn't really work. And then we can also figure out what the angle of rotation is. And so with the equilateral triangle, because we can rotate it into 3 different places, what we do, it's 360 for a full circle. So this rotation from here to here would be 360 divided by 3, which gives us how much?
120.
So that would be a 120-degree rotation. And you could actually rotate it this way, or you could rotate it the other way. It doesn't matter if it's clockwise or counterclockwise. So with the square, I'd be going from here to here, and from here to here, and it would be 90 degrees, because it's just 360 divided by 4, and you get 90 degrees. And then on this one, we would actually have 5 different places we could rotate it to. So you take 360 and divide by 5, which comes out to be 72 degrees. And we call this the angle of rotation. And then for the octagon, you would take 360 and divide by 8. And I'm not sure that comes out whole numbers. Let's work that out really quick with the calculator. So 360 divided by 8. Oh, it does. It comes out 45. I should have known that. 45 degrees. And so that is considered, when they ask for the angle of rotation, that's it. It's just basically, you think about how many turns you're going to make before you're all the way around, and you have to know that a full circle is 360. So 2 commonly used turns are half turns. So half turn is 180 degrees, a quarter turn is 90 degrees, which we talked about earlier. So a half turn would be like a half circle like this. That's 180. A quarter turn would go like that. So if you think about a center being right here, that's a quarter turn, that's 90. And then some other words that we're going to need to know, and this is going to help us when we talk about transformations. We're going to do some things to shapes. We need to know clockwise and counterclockwise. So clockwise is the way that a clock goes. It turns this way. Counterclockwise is the opposite of the way that a clock turns, and it goes this way. And then I suppose we should put on here somewhere that full circle is 360 degrees.